nossa próxima palestra ela vai ser em inglês. Então, nós vamos trocar agora a língua do evento para inglês. Tá todo mundo me ouvindo bem? Mariana, are you there?
Yeah, I'm here.
Okay. So let's continue with our school then. Mariana is our next speaker. I'm going to give a brief introduction about Mariana, and then we will shortly go to her talk. Mariana Afonso received her bachelor and master's in electrical engineering and computer engineering from the University of Porto, Portugal in 2015. She later received her Ph.D. in electrical engineering from the University of Bristol, UK in 2019. And during her Ph.D., she was part of the PROVISION ITN project funded by the European Commission. The project was conducted by leading video compression research groups from academia and industry and focused on the development of perceptually optimized video coding. Her joint contribution on video compression using spatio-temporal resolution adaptation was awarded at the Grand Challenge on Video Compression Technology at ICIP 2017. Mariana is currently a senior research scientist in the Encoding Technologies team at Netflix, which is responsible for developing and maintaining the encoding pipeline and producing all multimedia streams served to members around the globe. Furthermore, as a member of the Video Codecs and Research Group, she works on a variety of R&D projects on video encoding optimization, video codec evaluation, quality metrics, and development and research for next generation of video codecs. So I'd like to start. Thank you, Mariana, for being with us and give this talk. And the word is with you.
Thank you, Danielle. Obrigada. Let me share my screen. Can you see my presentation?
Yes, we can.
Yeah, thank you. Ok. Boa tarde a todos. Vou fazer esta apresentação em inglês, basicamente porque sinto mais confortável a falar de assuntos técnicos em inglês, mas no fim, se tiverem alguma pergunta que eu possa responder, eu posso obviamente responder em português também. Então vou passar para inglês agora. Thank you for inviting me to the DPVSA 2021. I'm really happy to be here. Thanks, Danielle, for the introduction. My talk will be on the journey towards better video compression for video on-demand streaming. I'm part of the Encoding Technologies team at Netflix. And yeah, this will be an overview talk on the role of the encoding technologies and also go deep diving a little bit on some of the aspects of encoding quality and standardization. So my journey to Netflix and to the US has been pretty interesting. I was actually born in Brazil. I was born in Rio de Janeiro. And I moved to Portugal when I was little with my family. And after I completed my bachelor's in Portugal, I moved to the UK and to pursue my PhD in video compression, which was pretty interesting and a really good time to be studying this area. Actually, when I started my PhD, I thought this was kind of maybe not a very hot topic, but I now realize that there's a lot of industry desire for engineers that works in this area. So yeah, it's really good. And then later I moved to the US to work at Netflix. So that this has basically been my journey around the world. Yeah, this is the journey so far. So I don't know what will happen in the future. So this is the Encoding Technologies. This is a part of the Encoding Technologies team at Netflix. As you can see, we are a pretty diverse set of people. We come from kind of different backgrounds as well. Some people are come from a more video quality assessment background. Some of us are more research oriented and others are more software oriented. Yeah, so the team has actually been growing quite a lot since I joined in 2018. And we're now about 40 people working on several different things related to the encoding at Netflix. So I'm not sure if I need to introduce Netflix per se, because I know it's pretty popular in Brazil. But Netflix is this huge streaming platform that brings lots of TV shows and movies to your living room or to your smartphones. And we have this huge catalog of stories that come from all around the world. So the role of Netflix is to bring great stories to all of our members, and the role of the encoding team is to make these stories as seamless, they have a seamless experience as possible, and to deliver the best possible quality in the video and audio that we deliver. No matter what device you're using to stream our content, whether you're on your living room with a fairly new like Samsung or LG Smart TV, or you're watching on your Google Chrome browser or Safari on your Mac, or you're in a mobile device on a train, for instance. The idea of our team and the goal of our team is so that anyone can have the best possible streaming experience without buffering or delays, or of course, without any crash in your content viewing experience. Now I'm going to go a little bit into some aspects of adaptive streaming. I'm receiving some notifications, but you can ignore that. And encoding, and this is not specific to Netflix, but it's, I'm going to give examples of how we do things at Netflix, but it's an industry-wide algorithms as well. So these are kind of the building blocks of Netflix streaming. These are really high level, an idea of how video and audio comes from production all the way to streaming on your devices. The first step, of course, is production. So we need to actually have access to the video and audio and subtitles from the content that we deliver. And production has been booming lately. The number of titles that are ingested in our system for the encoding has been increasing since a few years back. So we receive hundreds and hundreds of titles for encoding every day. And you can see that we've developed, the team at Netflix has developed a lot of really great shows recently. There's lots of seasons of The Crown. Lupin is a great example of a global sensation that comes from France, the French studios, Netflix French studios. But there's also been some really great Brazilian originals from Netflix, some nice TV shows, even some Christmas movies. So it's really exciting to see stories coming from all around the world coming to your TV. So once you receive these huge video and audio files that come from production, they are ingested into our encoding pipeline. And this is the part where our team handles the encoding aspects. And on a high level, the different stages of the encoding pipeline can be summarized as this slide shows you. The first one, of course, is, as I mentioned, is the source video that comes in. So these come in a variety of high quality formats, usually lossless or close to lossless formats. You can think about JPEG 2000 or ProRes, for instance. We receive these really high quality sources. And these are really large file sizes, right? You can't possibly stream them. So what we do is that we do all the encoding to be able to stream these in terms of over the internet, right? So the second step is the cropping and scaling and padding. So all the processing that is done to these sources. And here I'm skipping also some validation steps that we do to make sure that the sources are high quality and don't have any errors or artifacts. So yeah, this comes from all the processing stages. And then the interesting part is all the encoding. So one source generates multiple different encodes with multiple codecs, multiple resolutions, and multiple bit rates. And I'm going to explain a little bit on why we need to generate multiple codecs and multiple resolutions and bit rates later. But yeah, just knowing that a source video is translated into a number of different encodes for the same content. And then the next step is packaging. So from the elementary encoded streams, these are packaged into different container formats with audio, video, and time text, targeting different devices and different use cases. And in the end, we get the encoded bit streams that are compressed. They are much lower bit rate compared to the sources, and they are ready to be streamed to your devices through living room. So the next step is actually taking the streams and deploying them to our CDN, to our content delivery network. And Netflix has its own CDN, which is called OpenConnect. If you're interested to learn about OpenConnect, there's some tech blogs that are really interesting. I forgot to link them here, but I thought someone might be interested. So the OpenConnect network is a network of internet exchange locations, which contain all of our catalog in terms of video and audio streams, as I mentioned, and a number of caches that are available directly in the ISP locations that we partner with. So here in the map, we can see the internet exchange locations and also the ISP locations. So the idea is that you want to have the most popular titles and videos closer to the members so that you reduce latency when you stream. So this has affected a lot in our delivery in terms of not only costs, right, but also in terms of the quality of experience that the users will get when they click a button and automatically and really quickly get the video that they want at a really good quality. And then the final step is streaming. So this happens when you click play and your player will download all the streams that it wants and then depending on your throughput. Right, so here we're going to be looking a little bit on how adaptive streaming works, just some of the basics of adaptive streaming. So the idea of streaming is that depending on your throughput, so your internet bandwidth, the idea is to adapt the streams that you're downloading depending on your throughput so that you don't have to, or you reduce at least the amount of times that you need to buffer. So the times that you have to wait and buffer the content. So what happens is that when you have a low throughput, you'll usually receive a lower quality and lower bitrate stream for the same content. And for instance, as your throughput increases, you'll incrementally receive better and better quality until you achieve, for instance, the maximum resolution for your device type. Here, this is just a representation of a low, medium, and high quality for the same playback. And you can see in the different blocks that we're splitting it into different segments. So these are the segments that you're allowed to start decoding from. This is the only way that you can actually do the switch between the different bit rates and qualities. And if you actually take a look at each of the segments, you can plot these segments into quality and bitrate rate curves, and we call these the rate distortion curves. This is actually quality bitrate, but we call them rate distortion anyway. Yeah, so you'll see that these curves usually go up in quality as you are encoding with higher bitrate. And the idea is that you want to optimize your quality for the same bitrate. So you want to have your points as closer as possible to the top left of these curves. And you also want to do this on a global level. So for your entire playback, or you can consider an entire title. Yeah. So another concept in adaptive streaming in our content is convex hull. So imagine if you have different resolutions that you want to stream on. Usually you need to go lower in resolution to achieve certain bit rates as well. But there's also other reasons to reduce the resolution. So here there is a representation of 3 different resolutions: low resolution, mid resolution, and a high resolution. And you can see that these rate distortion curves are similar, but they are increasingly better. And then these are curves for the same content, right? So this is the same chunk or segment. Yeah. And if you combine these curves, you can see that at some points there are intersections between the curves. And these are points where you have the exact same bitrate and quality levels. And what happens is that you can take the convex hull of these points, and these will be the optimal points that you actually want to stream at. And what happens is that the high resolution curve usually intersects with some mid resolution, for instance, 1080p and 720p. There's a point where if you decrease your bitrate enough, so if you increase your quantization steps too much, then going lower resolution might actually give you better quality for the same bitrate. So this is an important aspect in video streaming. And Netflix encoding has progressed a lot throughout the years. Netflix actually started streaming video back in 2007. I think globally it was around 2008, but I have to confirm those numbers. But yeah, it was back in 2007, so that was a long time ago. And at the time, the encoding done in the industry was actually using a fixed set of resolutions and bit rates. And these are called bitrate ladders. And they were used, they used the same bitrate ladders across all titles in the catalog. And here are examples of bitrate ladders that you would see at the time. So for instance, this is on the left, we see a VC1, which is a pretty old codec. I think we retired that codec actually. So this is the first generation ladder for VC1. You would see that there's 4 different bit rates and 4 different resolutions. So each bit rate has a different resolution, and it goes up to 720p. And then in a modern, some kind of modern H.264 ladder, you would have bit rates up to 5.8 Mbps and up to 1080p. And then later on, when UHD was introduced for Netflix, so UHD, similar to 4K content, you would increase your bitrate and increase the resolution to 4K. As you can see, this is quite a simplistic way of doing encoding, since you're using the exact same ladder for all your titles. And let's see a visual example why this doesn't really give you optimal results. So here is a frame from, this is a kind of, I think this is some Avengers movie. And this is an action scene. You can see that it's encoded at 1050 kilobits per second at 1080p. And you see a lot of blocking artifacts. There's lots of blurring. There's not a lot of detail kept in this scene. And here, this is a contrasting example. This is an animation. This is Futurama. And it's also encoded at the same bitrate and at the same resolution. And you see that the quality looks pretty good. I don't know how it looks on your screen, but yeah, it's pretty flawless from where I'm looking at. And if we go back to the scene, the action scene, and you increase the bitrate by 5 times, you'll see that the quality is much better. So you see a lot more representation of what the scene is, what's happening. And if we go back to the animation scene and increase the bitrate again by 5 times, you'll see that it barely changed. So I'm going back and forth between the animation at 1050 kilobits per second and 5000 kilobits per second, and it's barely noticeable any difference. So let's go back. So actually what is happening is that this, you're actually wasting your bitrate by encoding this, if you're encoding this animation sequence at 5,000 kilobits per second, I'm sorry, you would actually be wasting a lot of bitrate. So you don't need that much. This is why it's not optimal to always use the same pairs of bit rates, resolutions for your entire catalog. So from 2007 to, there's been some updates in the meantime, but the biggest update was in 2015, where our team launched per title encoding. So this means that different ladders were used for different titles, and this was the ladders, the determination for the ladders was based on an estimate of the title's complexity. So there was a pre-encoding stage where you would actually do some encoding and estimate what the complexity was for that title, and then you would generate a different ladder for each title. So there was a lot of savings from this point. And then in 2017, our team launched per shot optimization, which meant that you would do the optimization on a shot level based on the actual shot complexity. So this is much more complex in terms of pre-encoding, as you actually need to encode your shot or each shot of your title at multiple bit rates and qualities, and then determine what the best optimal path was. So I'm going to be talking about this next as well. And the result from all of these optimizations is a huge impact, is a huge improvement in the encoding of the titles at Netflix. So here we see the different generations. So in addition to different optimizations, this plot also shows kind of also different codecs. If we don't consider the multiple codecs as well, we see that there's a huge difference between the first per title encoding and then the per shot optimization. And then of course, if you move to a better codec like VP9, you would get even more improvements. And the idea of per shot optimization is to give more bitrate to scenes that actually give you a reward for that bitrate. So if you consider the rate distortion curves, if you see a flat region, for example, which you would probably get in the animation scene, it means that as you add more bitrate, you don't see an improvement in quality. But if you consider scenes like that have a lot going on, for instance, in this peak here, it means that if you increase the bitrate, you would see a lot more benefit. So the idea is to modulate this so that you would get your best optimal operating points on the quality bitrate curve. So this is a representation of the per shot optimization. This is a matrix of QP versus shot. So for each of the columns, we encoded at different QPs, and we do this for every shot. And we get the quality and bitrate for each of these combinations. So you can consider that there's two, if you consider a path going from each of these shots, you'll see that there's two two initial points that you can determine, the red and the green point here. The red means that you're encoding all the shots at the highest QP that you operate, and you get the red curve, which will give you the lowest quality and bitrate. And then you have the green one, which you will use the lowest QP, which means the highest quality for all shots. And then all points in between, you can imagine that you can draw different paths among these QP combinations, and you'll get different points in this curve. So you can think, okay, let's just do all the paths, and you can get multiple points and then do the convex hull. But there's too many shots, so you can't do that. But there's a simple way to solve this problem using an iterative algorithm that uses the slope. So this is what we use. So in the end, you'll actually get a rate distortion curve with the global optimal points in the quality versus bitrate trade-off. And in addition to QPs, you can also do this on different resolutions as well. So you can have a high resolution, mid resolution, low resolution, or as many resolutions as you want, of course. And as I said, you can compute a convex hull, and this could be a convex hull of your global optimum for the title. And then after you compute the best operating points, you also need to decide what are the best points in the ladder to actually do your encoding and streaming. So this is a subsampling of the points in the quality bitrate ladder. So in addition to improving encoding optimizations, of course, our team has also incorporated different formats that allow for more immersive viewing experiences. So the first one that I already talked about was 4K. So 1080p is fine for the majority of viewing, but it's not ideal for, of course, if you're watching on your living room and if you have a really high-end device. So you really want to get the best quality possible, and that gives you, 4K gives you much higher detail, and it's widely supported now by a lot of consumer devices. And another aspect is standard dynamic range or high dynamic range. So Netflix supports two formats for HDR, high dynamic range, HDR10 and Dolby Vision. And HDR will give you better color representation and more distinct distinction between light and dark scenes. It just gives you a better overall experience. Netflix supports these features under a premium subscription, so you need to pay an additional subscription to be able to access these streams. And there's also been a lot of innovations in encoding of 4K and high dynamic range using per shot optimization as well. So you can see I linked here on a tech blog, a recent tech blog on optimizing 4K encoding. In addition to all of these new changes that are pretty exciting, the problem with that is that not all devices are able to actually benefit from these improvements if they have some hardware limitations. So we, as I mentioned before, we support a huge variety of devices. There's thousands of device types that need to be supported, and each of them needs to be compatible with one of the encode families that we produce. And in fact, the per title encodes that were launched in 2015 that use H.264 main profile, they're still served to a number, like a big number of members, increasingly less, but they still represent a substantial portion of view hours and traffic. And therefore, last year we wanted to do some innovation and improvement to these specific encodes that are targeted to these legacy devices, if we can call them legacy. So we expect these to have we expect these to have a tremendous benefit for our members as well. And then the aspects that we needed to consider for this effort were fivefold. The first one is we want a reduction in bitrate or traffic at the same visual quality. So at the same visual quality, you want less bitrate. And you also want a reduction in your footprint. So this is the storage that the different representations of the same content of the encodes take on our CDNs. So that the lower the storage requirements, the better, the more content we can have in caches that are closer to the members. And this is related to bitrate, but it's also related to the number of representations we have for the same content. So it's related, but not the same. And we also wanted to improve quality of experience. And this means improving metrics like rebuffer rates, time to achieve a certain quality, among other metrics. And the most important thing that we wanted to do is maintain device compatibility. So if any of these device types would not be compatible with any changes that we do to the encodes, then none of this would be worth it. So that's the last thing that we need to consider. So we launched these improvements last year, and the difference between the per title encodes and these encodes is that in addition to having a better strategy for bitrate allocation, using a multipath strategy, we also are using VMAF to drive encoding decisions, which was not used back in 2015. And then there's also been changes that allow for more consistent quality over the title's durations and changes to the bitrate ladder operating points. Yeah, so here is an example of the bitrate and quality variation over time and over different chunks of the video for the per title encodes and for the improved encodes. And we see that for the per title encodes, for each chunk, we are streaming at the same average bitrate. So this was the how the per title encodes worked. And you can see that the problem with that is that there are some quality drops depending on your chunk, if the chunk is very complex to code, as we mentioned before. So the improvement is that for the improved encodes, we now allow the bitrate to vary depending on the chunk, and this gives you a more consistent quality over time, as you can see in the bottom plot here. We ran this in addition to, of course, the offline tests that we can do. So we can compute BD rates, which are a measure of the benefit that you have percent-wise in your rate quality curves. You can also compute storage and do the storage analysis. But the problem is that any change that we do to encoding, like most changes, we need to run actual tests in the field with members that will experience these streams, and these are called A/B tests. So we run a control set with different members, and we run a test set with other members that actually receive the test. And we measure a variety of QE metrics, like BB buffers. We measure the bitrate over the different sessions and other things. So this also measures not only the encoding side changes, but also streaming side, so adaptive streaming changes that we do. So these improvements, we can see here like an average improvements that we saw with these changes. For instance, the average bitrate per session was reduced by 20%. Average rebuffers were reduced as well, 10%. We saw the same average quality or pretty similar average quality. And we saw also reduction of 20% on our CDNs for these specific encodes. Yeah, if you wanted more information, we have them, a lot more information on our tech blog. Okay, now we're going to talk about measuring video quality. So we talked about encoding, a lot about quality and bitrate trade-offs, but we didn't discuss how we actually measure quality at Netflix and of course in other industries as well. So we need a reliable objective metric to estimate quality. There are two types of metrics that you can use. You can use a subjective metric, which implies that people are actually looking at the streams, but I don't think any of us have time to actually be looking at all streams that are generated in my pipeline. So we actually need an objective metric that is fast enough to run at scale and that tracks perceptual quality reliably. Not only, for instance, the distortion between the original and the compressed video. So this is where VMAF comes in. VMAF is Video Multi-Method Assessment Fusion, and it was developed by our team a few years ago, and it's been really useful for improving our streaming on Netflix. And it's also open source, so a lot of other companies are using it, and it's a really good open source community, and it's good to also give feedback and get feedback on different improvements to VMAF. So VMAF models low-level aspects of the human visual system by computing some low-level features in both the reference and the distorted videos. So it's a full reference metric. And it has also been trained by collecting lots of subjective data from in-lab tests. And it uses a machine learning model to correlate the features with the subjective data to fuse them into a single metric for your video. So this is how it's been trained. There's a lot of papers on VMAF if you're also interested as well. So one thing that it leverages is a concept called contrast masking. And this is when the concept that you actually see less artifacts when they're superimposed in signals that have similar frequency orientation. So for instance, if you have lots of coding artifacts in texture regions, you can usually perceive less. visually these artifacts, and if you have artifacts in homogeneous regions, like the ones that are highlighted in the picture here. And VMAF was designed to account for encoding artifacts specifically. So these artifacts are generated by both compression and scaling. As we explained before, that we use multiple QPs and multiple resolutions. So we get a combination of these artifacts, and this is what VMAF has been trained to address. And the also important aspect of VMAF is that we trained it to account for different genres as well of video. Mostly, of course, a pristine video, not user-generated video, although it can also be used for user-generated video. It was trained on content from our catalog in different content types. So, for instance, animations, scenes, and drama, dark scenes, lighter scenes. So the idea is that data will drive the metric to improve. And if you don't have a certain type of content, then of course your metric has never seen this before. So you would get lower scores or lower correlation with subjective scores. Yeah, so here we see a comparison between PSNR and VMAF, in which PSNR gives you a really high value for the left frame, and it gives you a pretty bad score for the second frame, although visually these are probably similar quality, and VMAF gives a pretty similar VMAF score. In terms of how VMAF works internally, I briefly mentioned this before. VMAF computes a number of spatial and temporal features, low-level features on the reference and the distorted video. So it computes the two spatial metrics that it computes are the elementary metrics VIF and DLM. So these compute loss in quality and loss in fidelity. And there's also a temporal feature which called TI, which is just the frame difference between two adjacent frames, and this will measure the amount of motion that you have in your scene. These are combined on a frame level with spatial pooling, and the training results from the subjective data or generate a model that you can actually use when you want to get a VMAF score. And the fusion metric, the fusion method is an SVM. So it's one of the machine learning types. And you can actually fuse your training scores to predict your final per score frame. And then in order to get a score per, for instance, per shot or per chunk or per title, you can do spatial pooling. So there are different types of pooling that you can do. You can do an average pooling, you can do harmonic, geometric, or other types of averages. Yeah, so this is how you get the score for VMAF. And interesting thing is that VMAF also, like other metrics, has some assumptions. So one of the assumptions that VMAF has is a viewing distance assumption. So it assumes viewers are sitting in front of a 1080p display at a distance of about 3 times the height of the display. So this is around 60 pixels per degree. If you're sitting closer to your monitor, you would expect VMAF results to to over-predict the quality. And if you're sitting further apart, you would expect VMAF to be not as accurate, since you're not viewing it from the distance that it was trained on in the subjective tests. So to account for the differences in this, VMAF also provides models for 4K, and there's also a phone model for smaller displays. But VMAF is great. We know it's open source. There has been a lot of improvements, but there are always room for improvements in anything. So there's ongoing research within Netflix and with our academic collaborators on multiple different areas for VMAF. And some interesting improvements lately and ongoing improvements are more robust temporal features. We'll search for temporal features that are a little bit more complicated than the ones that VMAF is using, but will give you a higher return. and better correlation with subjective scores. Also, the handling of noisy sources is pretty tricky for every metric, but VMAF is also not that accurate when you have a lot of noise. And the last two that I wanted to discuss, I'll talk about, are enhancement gain and banning artifacts. So VMAF was designed, as I said, to account for scaling and compression artifacts, and it's a full reference metric. But it is known that some enhancement techniques, for instance, sharpening and historemicalization, can actually boost the VMAF scores when there's not a lot of perceptual gain coming from these techniques. So they can boost the score on top of the score that you would get for the actual original. So we call this enhancement. And in order to avoid this issue, for use cases that actually only want to measure the difference between your original and your distorted video, our team has launched, changed recently and added a model called VMAF-neg, which stands for no enhancement gain. And this has been recently introduced, and it's actually being used for standardization and for other efforts as well. So the problem with enhancement gain is that here we see an original source. This is a KEO, pretty used sequence in video codec development. So the original is on the left. What we did in the middle is to sharpen it using an unsharpened filter with some level. And if you compute VMAF, you'll see that it goes over 100, which is the maximum VMAF that is usually allowed. So it's 112. And visually, it might look a little bit better, but you can actually sharpen it even more, and you would get really distorted video, and VMAF would keep increasing. So you can also do other types of pre-processing called, you can also do historemicalization, which is seen on the right, and you would really get a really high VMAF score. So this is why our team has introduced this VMAF-neg metric, which is actually measuring the distance between the original and the distortions that you get in the distorted image. And in the middle, you see that the VMAF-neg score is 85, and for the historemicalization image, it's 79. So it actually will not account enhancement as one of the aspects in the metric computation. And then the last thing I wanted to talk about in terms of quality measurement is banning artifacts. So banning artifacts are really annoying artifacts that show up everywhere. You can see them on YouTube videos, on our platform even, and on other services as well. And these are perceptually really annoying, but really hard to detect using regular quality metrics, including VMAF and even PSNR. They're not sensitive to these artifacts. So one reason, the reason that they show up is usually when you have regions with low gradients, and you have like a really large region, like the one that we see here. And they show up usually for different causes. The content can be prone to banning artifacts, like the one that we're showing here. They can be generated if you convert a high bit depth video to a really low bit depth video. You can also get banning artifacts. Compression always makes banning worse because it reduces the noise that you have. You cannot code noise as well as you code low-level frequencies. And you can also get banding if when you downscale a video and upscale. So scaling also promotes banning artifacts. So our team has been working last year on a banding metric. And the first step to actually developing this metric was to gather subjective scores. So we did a subjective experiment for 8-bit videos. We had a total of 86 videos that we gathered. Some of them had banding, some of them didn't have banding, some had banding in some regions and not banding in other regions in the frame. And we asked a number of participants to rate the videos on a scale from 0 to 100. And actually, we didn't ask them to rate just the quality of the video. So if the video has good quality or bad quality, we asked them to rate the impact of the banning artifacts. So if the banning artifact was very annoying, unwatchable, or all the way to imperceptible, which means that there is no banning artifact. So we developed last year, and we are still improving this year, a banning artifact metric called CAMBI, which stands for Contrast Aware Multi-Scale Banding Index. And the way it works, like really high level, we have tech blocks if you want to go deep into the algorithm and in the paper as well. So it works on three different steps. The first one is a pre-processing step. Then there's a multi-scale banding confidence, which is computed pixel-wise, and you get a few different maps on different scales. So this is why it's a multi-scale algorithm. And then in the end, there's spatial pooling to get the final score. And in terms of the way that it computes the banding confidence on a per pixel level, there's a window in which it computes the confidence that the pixel is on a neighborhood which has banding artifacts. And this method is working for 8-bit videos, and we also have support for 10-bit videos, which is mainly our use case in Netflix. So given the subjective scores that we had and the development of CAMBI, we can compute the correlation with the subjective scores. And we can also compute the correlation with VMAF and PSNR. And as you see from the plots, there's barely any correlation with the subjective scores for VMAF and PSNR, which means that they really cannot capture these artifacts. While CAMBI is highly correlated with the artifacts, with the MOS scores that we got from the tests. So the correlation for CAMBI is reported over 0.9, which is pretty high correlation. Yeah, and you can see more details in our PCS paper from, yeah. And since the first version of CAMBI, we also been optimizing it and improving it. So from the first version, the correlation has been improved by about 0.03 in terms of SROCC and PLCC correlation metrics. And we recently launched a tech blog explaining CAMBI and explaining all of these things. And we also open sourced CAMBI recently together with VMAF, so you can find it also as a feature, standalone feature in the VMAF repo. Our hope is to improve VMAF by incorporating CAMBI, but this is future work, and it's actually ongoing work, but yeah, it's for a future version of VMAF. So the last topic I want to touch on is video standards at Netflix and the role of video coding at Netflix. So as I mentioned, to support a diverse landscape of client devices, we have and maintain in our service a number of codecs. And we know that innovations in compression efficiency of newer codecs, as I showed in the plot that I was showing before with the .264 and VP9, they have potential to translate into much better viewing experiences for our members. And for this reason, we have always moved really quickly in adopting newer standards. And the problem is that adopting newer standards and participating in standardization is good. But the problem is there's a lot of external factors as well when it comes to adopting newer codecs. So we've also been big in influencing and trying to influence the industry to adopt newer codecs so that everyone can benefit from these improvements. So one of the efforts that we've been working since 2015 is the Alliance for Open Media, which was founded in 2015, and it's usually called AOM. And the goal of AOM is to produce royalty-free media standards, and Netflix is one of the founding members. The first format published by AOM was AV1, and it was released in 2018. So for the AV1 development, some of the highlights that our team has worked on is delivering, like sending source material for the common test conditions. So working on the testing of the tool development, also contributing a normative film grain tool, which was contributed by my colleague Andre, and also contributing to the decoder model for AV1. So just a few words about the film grain. We at Netflix, we have a lot of sources that have film grain, and film grain or sensor noise is sometimes added artificially by digital post-production because some directors like the look and look of film grain. So it's not always present in the original source, but we want to preserve creative intent on Netflix. So this is one thing that we are passionate about. We actually want the intent of the creators to shine through and get all the way to your streaming devices. The problem with film grain is that it's really, really difficult to compress with current video coding standards, and because it has a high temporal and spatial randomness to it. So it's really challenging. So one of the alternatives that has been proposed and was adopted in AV1 is to analyze and synthesize the film grain. So how it works is that there is a denoiser in the encoder, and this denoiser is non-normative, which means that any encoder can choose what denoiser it's using, and so it's not part of the standard. And the denoiser is added to the encoder to create a denoised video, and then the residual between the denoised video and the input video is used to estimate the film grain parameters that are sent to the decoder side. And the encoded video is generated only from the denoised video. So at the decoder side now, we get the decoded video. We of course decode it, and we add the film grain synthesized at the decoder side. So this has two type of benefits. The first one is that you don't encode the film grain at all. So this makes your life a lot easier. So you can actually decrease your bitrate by quite a lot and actually get a really good quality. And in the end, you can synthesize really good quality film grain. So you would get the best of both worlds with this tool, if this tool is enabled, of course. So here we see a visual example of synthesized film grain. And this is on the left. The video has been encoded at 6 Mbps with no film grain. So you actually don't see any film grain in your output, even at this high bit rate. And on the right, you see a synthesized film grain at 2.8 Mbps, which is pretty good. If you would actually want to code this video with film grain, you would probably need, I don't know, maybe 10 times the bit rate that you actually have here. So this is why we see lots of benefits from this method. In addition to the codec development, Netflix has did initial deployment of AV1, which is really exciting in 2020. So it was launched to first to some Android devices that first received AV1. And since then, there's been some more devices that have been allocated to AV1. So maybe you're even watching AV1 when you're using your mobile phone right now. And there's been a lot of ongoing testing on a number of additional clients with both hardware and software decoding solutions. And then another of the goal for the AV1 productization is to expand AV1 catalog coverage and to improve the encoding algorithms that are used for AV1 in addition to the algorithms that we already have for other codecs. Yeah, and we also been supporting a number of open source projects on the improving productization of AV1, including some projects for David, which is the software decoder for AV1, and some GPU-assisted AV1 decoding with other companies. So the goal overall is to extend the AV1 coverage over the next year, so hopefully everyone gets better video quality at lower bit rates. So there's, in addition to having to, developing these codecs, needing to productize these codecs in our system, there are a lot of challenges that come with productizing a codec. Just wanted to touch on a few different aspects and trade-offs that are involved in this effort. So the first one is in terms of the client side. Of course, we need to the clients to have critical support of the codec. And this is for video or images, right? And in addition, there needs to be certification of the specific codec and encoding settings. So even though a device manufacturer might tell us that it supports this codec at this level, this profile and this level, we need to verify that this actually works to be able to certify devices. Then on the delivery network side, these new streams, every time we create new streams and new encode families, which we call them, we need to, they need to coexist with existing representations of the same content. So they actually fight for space in the caches that we have. So the more that streams that we have, the worse it is for the content delivery network. So we need to be aware of that as well. And then the final thing is encoding. So encoding is not cheap. So we have a huge catalog and there's a lot of variety in the titles that our members watch. So to actually have a good coverage of the catalog, you need to do a lot of encoding. So most of these profiles, sometimes you need to do a backfill or encode again, titles that are older because they're still popular. So this is another aspect of productizing codec. And in addition to video, our UI also contains a lot of artwork. And this artwork is, the idea is to have really good quality artwork. And in order to be able to download these quickly, although these are images, right? We are always looking for ways to optimize the encoding. So one way is to use a better codec. So JPEG has been used forever, but there are many other image codecs out there. And one that we see huge benefits is AVIF, which is the AV1 image file format. And it's a container format for AV1 intra-coded images. And we see from our tests that it's more efficient than HUVC intra. And it has an additional features that make it pretty attractive for using in our UI. For instance, it has support for lossless alpha coding, also for animations, and it can support HDR metadata and color gamut. So yeah, so there's a tech blog recently on support for AVIF, which the problem again is that it needs to be supported by devices. And we see that some major browsers have already supported it, for instance, Chrome, but we expect more clients to support this in the long run so that we can maybe move to AVIF in the future. And then just wanted to touch a little bit on the performance of AV1. These are tests that we ran in 2019, and we see a huge benefit of AV1 compared to other codec families. And these are results that we have been achieved by encoding 1080p titles. And these use the per shot optimization that we mentioned before. And we didn't have film grain synthesis on for these results. And we see compared to the H.264 encodes in terms of per shot encodes, we see savings of around 40% in terms of bit rate. So for the same quality, we see 40% lower bit rate. So this is also a huge gap between VP9 and AV1. So this is why we want to increasingly move to streaming AV1. And then the final piece of the puzzle is the standardization efforts beyond AV1. So We talked about encoding optimizations, quality, and adopting newer codecs. And our team also works on efforts beyond the current codecs. So research has actually started now for earlier this year for the next generation of royalty-free video codecs from Alliance for Open Media. And so new tools are currently being evaluated based on the common test conditions that were defined by AOM for this effort. And we're happy to say that VMAF is one of the quality metrics that are used to assess quality of these tools, in addition to, of course, PSNR, which hasn't been the only metric used for standardization in the recent ML standards. And it's also interesting that the common test conditions for AOM also include adaptive streaming test conditions, which are more in line with the use case that we use. So we are confident that the outcome of this research and outcome of this standard will translate into benefits for adaptive streaming. And then, so there's been a lot of contributed tools by member companies, but this is an ongoing phase that will last a few years. But hopefully soon we'll get a new codec in addition to AV2, AV1, and then you'll have the effort of course, having them into clients and then deploying them into Netflix. So hopefully, I don't know the exact timeline, but in a few years, we'll be able to stream this new codec. Thank you. I'm happy to take any questions as well. Thanks for the attention.
Thank you, Mariana. Can you hear me well?
Yeah, I can hear you.
Okay. Thanks for your talk. It was very interesting. Actually, I have a big community here working with video coding, so I bet we have some questions for you here. Let me see the Q&A. So here we have a question from, we have a lot of questions actually. Let me start from the beginning. I'm kind of lost here. Yes, here. Professor Carla Pagliari is asking, thanks for the excellent presentation. Will Netflix ever do live sports? Does Netflix offer support to the AV1 codec only to Android platform? That's her question.
Okay, in terms of the first question, live sports, there's been a lot of talk on live sports, but I don't think that will be the near future for Netflix. It might happen in the way in the future, but I think we're focused on video on demand for TV shows and movies. And we've also been launching games. So I think that's the next thing that is happening for Netflix. So live streaming might be maybe way in the future, might not even happen. And then the second question was about AV1.
Yes.
I'm not sure if we have AV1 support for other devices other than Android right now. I know we've been testing a lot of device types, including, for instance, Samsung TVs, but I'm not sure that's out there yet. So there's been a lot of changes recently, but hopefully we'll have a lot more devices soon. I think that there's a tech blog coming on AV1. So if you want more information, be sure to check the Netflix tech blog. I think there's a tech blog coming from our team really soon on that.
Okay. Mateus Grelert has a question. Thank you for this enlightening talk regarding the footprint aspect that you want to minimize. How does Netflix transcode different QP and resolutions for adaptive streaming? Are they all pre-encoded and stored? Do you even encode some resolutions on the demand to avoid unnecessary storage? That was actually one of my questions. I don't know if you got it.
Not sure if I fully understand the question.
If you have for all streams, you have them pre-encoded and storage and stored them, or do you have any kind of dynamic? Dynamic transcoding for the different bit rates and different resolutions.
Okay, so what happens is that there's a pre-encoding step that is used to determine what would be the optimal per shot encoding. So all this pre-encoding is a huge effort, right? There's a lot of encodes done, but that is not stored. So we don't store that. So that is only used for calculating the quality and bit rates. And then you do, you have all of these quality and bit rates, you compute the global optimum points, and then you pick a few of them that you're actually going to stream. So the footprint aspect is on the later end. So once you have all the pre-encoding done, the subsampling that you actually do to your optimal encodes are what will account for the footprint. So these are the streams that will be available on the client side. So not all the encoding that we do is available for the clients to stream. So only a subset of that. If that answers the question.
Sure, but there is no dynamic transcoding then. I mean, if there is any bit stream that's not available and it's generated while the video is on demand.
So there's a few cycles of streaming. So there's, as I said, there's many encode families, and sometimes there's improvements, and you would get more streams. But I'm not sure what, if there's a dynamic transcoding as what you mentioned. Yeah.
Okay. Vanessa is asking, hi Mariana, nice talk. I remember last time we met at MPEG, you were proposing a machine learning related technique to VVC. Since then, Netflix has contributed to VVC, or now all efforts are more related to develop and promote AV1. Are there plans to stream VVC? Beijos.
Hi, Vanessa. Yeah, I don't know. Right now, I don't think we have a plan for VVC yet, because we, as I said, we're committed to the Alliance for Open Media, and we now have our plates full with deployment of VV1. So I don't think there's a horizon yet for VVC, but yeah, I don't know how to comment on that. Maybe at some point, but yeah, not now.
Okay, we still have time. Guilherme says, thanks for the amazing talk, Mariana. Do you consider creating encoding setups and bit streams representations that optimize the use of computational and energy resources at the decoder side?
Yeah, so we've been doing some optimizations actually on that. So let me give you some context. So of course, the priority is to give you optimized streams, so no matter how complex it is to do the encoding. But of course, we noticed that we have been getting a lot more titles lately, so the catalog has increased a lot. So we need to be actually aware of the complexity that it takes to do all this encoding. So our team has done a few efforts to reduce the complexity by optimizing a little bit we're reducing a little bit the pre-encodes in a smart way. We don't have a publication yet, but there's current efforts. So hopefully we'll get something to share soon on that. But that's of course on our mind as well. Yeah.
Okay. Mateus is asking again, is Netflix considering to include NAN-based metrics like QL, PIPs, and even codecs in its research portfolio?
Can you repeat that question? I think I heard it really well.
I don't know if my micro is working okay. Is Netflix considering to include NN-based metrics like LP, IPS, and even codecs in its research portfolio?
I don't think so at the moment, but we have to explore that. That's something we've been considering, but we haven't explored it internally yet. Yeah, maybe in the future. But that's a really interesting point.
Okay. Now the Q&A here. Kevin is asking about VVC. You actually already answered, but he's asking also about the upcoming AV2. If you can give a share of it for us, for the development of AV2, Netflix.
So our AV2, as I mentioned, is in a research phase. So it's currently accepting candidate tools. It started earlier this year in January, and our team has been trying to contribute as well. One of my colleagues is the co-chair for the codec working group, Andre, and we've been involved in the effort. So hopefully we'll be able to contribute new tools and other companies as well, so that we can actually have a successful AV2 codec at some point.
Okay, nice. Bruno is asking, actually you already answered this one, I guess, but per shots encodes outside the optimum convex hole are discarded. I think you answered, you said yes, right? Only a few points of those streams are actually stored, right?
Yeah, yeah.
Okay. Iago is asking, is Netflix using any hardware accelerators such as GPUs and FPGAs on the encoding of its titles? Actually, this was one of my questions as well.
I think there's been some research efforts recently to get some hardware encoders, but we currently don't use hardware encoding. I know some companies use lots of FPGAs for encoding video, like I think Facebook. But yeah, we currently don't use. But I think we've been exploring some hardware encoders as well.
Sure. And now he's asking, I guess it's a question that is interesting for everybody here in the audience. When considering companies like Netflix, how likely are they to hire someone with a PhD in the area, but without any industry experience?
I think highly likely. I'm sorry.
This is good news for everybody here, I guess.
Yeah, I think highly likely. If you're motivated and if you want to work in this industry, I think there's a lot of opportunity, not only at Netflix, right, but other companies as well. And I see this this industry is blooming right now. There's a lot of need for good engineers and also good researchers. So even if you are not in this area in terms of research, if you're in an adjacent area, there's also lots of opportunity. So I would say yes.
That's nice to hear. And finally here, Professor Agostini is asking, what are the channels for collaboration between Netflix and Brazilian researchers? Is there any possibility of collaboration?
Yeah, we collaborate with a lot of different universities around the world currently. So our team, I don't know how many, but it's probably over 5 different industry collaborations. And we've collaborated with other universities in the past as well. So VMAF also came from a university collaboration with a university here in the US. So if you're interested in trying to collaborating with us, just shoot us an email. If you have any good ideas or a project that you want to work on, we are happy to listen and talk, and perhaps we can explore a joint project together and we can work together. Yeah.
Nice. I guess I picked up one last question here from Professor Carla. Netflix uses the same segment duration for all content bit rates?
The segment duration of the video, no. So it depends on the encode family, as we said with the shot encoding. Well, it depends on what you mean by segment. But yeah, it's a variable segment sizes depending on the encode family.
Okay, nice. I guess that's all our questions. I mean, your talk was really interesting for us because we have lots of Brazilians working on encoding and decoding in this area. So I'd like to thank you again for giving this talk in our school. I guess we have a little break now, right? 15 minutes until the next talk. Actually, is the poster session that will start 4:30. Yes. Então, obrigado, Mariana.
Obrigado.
See you.